Okay, so let's start talking about what sound is in a little more practical detail. Sound is the result of the vibration of molecules in a medium that is created by changes in pressure. Most of the time, that medium is the air, like the air in this room that I'm recording these slides in. Sound is also transmitted through liquids and solids, so you can hear sounds underwater. You can hear sounds through walls. The differences in density and elasticity of the medium affects the speed of sound. So when we talk about the speed of sound for some of the exercises we'll do in class, we'll always or almost always be talking about the speed of sound in air. To give you a little bit of an idea of what a sound wave would look like if you could see one, there's a GIF image on a web page here. Okay, so on the left side of this image, there is a red bar that's meant to be like the surface of a speaker. So if you take the little foamy thing off of a speaker, like a big one, you will see basically a plate underneath. That plate vibrates and pushes air molecules around, and that vibration then is what creates sound waves. If you look at all of the little black dots, that's the medium. So those are supposed to be the air molecules that the sound is propagating through. And if you look at that word wavelength and the dotted lines, those point up at places where the black dots are higher density, are clumped together. Those would be high pressure points. And you notice as that word wavelength moves from left to right, those black dot clumps also seem to be moving left to right, or propagating is the term that we will use in acoustics. Now we also have a few individual red dots up there. Those are specific individual air molecules so that you can see the behavior of the individual air molecules versus the wave. So the molecules themselves are just vibrating back and forth. They're shifting a little bit left and right on the basis of the propagating sound wave, but they don't travel along with the wave. So the wave itself is a change in pressure or a change in air molecule density that propagates through the medium, but it doesn't bring all of the air molecules along with it. They vibrate more or less in place. Last but not least, on the bottom of this thing, we have a sound pressure waveform graph for this wave, which is something we'll be talking about again a little bit later in this lecture. Okay. Sound waves are a type of wave called a longitudinal wave, where the molecules in the medium get displaced in the same direction as the propagation of the wave. So the little red dots were kind of rocking back and forth left to right with the wave that was propagating from the left to the right in that image. So we have this displacement of air molecules in the medium that create changes in pressure. So we'll talk about air pressures when we talk about speech. Those air pressures can either be higher than normal, where the molecules are clumped together. It's also called compression. Or that pressure can be lower than normal, also called rarefaction, where there are fewer molecules filling up the space. There is another type of wave out there in the world of physics called a transverse wave. Transverse waves have the displacement of the molecules in the medium perpendicular to the propagation of the wave. So as the wave is traveling from left to right, for example, the molecules in the medium would be going up and down. So you see waves like that when you're doing things like swinging a jump rope or you pluck a guitar string. Water waves are more like these transverse kind of waves. If you see something floating in the water as waves go by, that thing floating will mostly bob up and down as the wave passes by it. It doesn't get completely carried along with the wave. To make that happen, you have to do extra stuff. Like that's how surfers surf. They do things with the surfboard to cause them to be carried along with that transverse wave. Even though we can't see them, or for that matter, hear them doing it, molecules of air that surround you are constantly moving around. They kind of bounce off of each other randomly in a pattern called Brownian motion, presumably named after some physicist named Brown back in the day who figured this out. The number of collisions that happen is related to the density, and this is what causes the air pressure. So as a bunch of molecules gather together and collide, there's higher air pressure. If there aren't very many molecules around to collide, there's lower air pressure. Air pressure on Earth is related to altitude. So up here in Boone in the mountains, we have a lower air pressure than they do down at sea level by default. But we're going to ignore that for everything that we do in this class. The standard measurement of air pressure, the atmospheric pressure at sea level, is about 100 kilopascals, so 100,000 pascals. Because that's a pretty big number with a lot of zeros on it, it's much easier for us to refer to relative changes in air pressure from that atmospheric pressure. So pressures that are above 100,000 will be positive air pressures. That will be cases where there's compression. Pressures that are lower than that 100,000 will be negative air pressures. That will be rarefaction. So we might have things like plus 10 pascals for compression or minus 10 pascals for rarefaction. A lot of the tables that you may have seen in, say, anatomy, or that you'll see in this book, will probably use centimeters of water as their measure of pressure. But it'll be the same thing, where 0 is atmospheric pressure, kind of the basic pressure where nothing special is happening, and that can go up when air molecules get squished together, or go down when air molecules are spread apart. Air always tries to move from higher pressure to lower pressure if it can, always tries to get back to a state of equilibrium where everything is at atmospheric pressure. That difference in pressures is going to cause air to flow. So this is where we get things happening for speech, for example. The lungs shrink. That compresses the air molecules that are inside the lungs, putting them under higher pressure. If those air molecules can flow out to the outside air in the atmosphere, they will do that to try to return back to atmospheric pressure. We can measure that moving volume of air in terms of a rate of flow, how much air gets moved over a period of time. Pretty standard unit used for speech, because it's related to respiration, is liters per second, something that, again, you might have seen in your anatomy and physiology class. When air is flowing, say flowing out your mouth, the size of the opening that it's flowing out of has an effect on how the air can flow. The flow can be very smooth if the opening is big enough for the air to kind of get out without much resistance. That's called laminar flow. That happens when you're breathing quietly. The flow can become turbulent or not smooth if there's a large amount of air being forced through a smaller amount of space, and that turbulence generates noise. That's one of the ways that we make noise for speech sounds, in particular for the sounds that are called obstruent consonants. Obstruent because an obstruction to the airflow helps make their noise. Air movement due to sound pressure happens at the individual molecular level. So as we have a sound wave propagating, higher pressure from that propagating sound wave squashes air molecules together, but those air molecules want to spread back out to atmospheric pressure. But because of physics things like momentum and inertia, that process of spreading out will go too far. The air molecules will get too far spread out and will have low air pressure or rarefaction. Air molecules then will fill back in to try to get to that equilibrium. But once again, because of momentum and inertia, they'll overshoot, and this cycle continues, so we get a vibration in the air molecules, an oscillation between high and low pressure that happens on the basis of momentum and inertia applying to air molecules. This whole process can also start with low pressure. If you have a low pressure area, then air molecules rush into it. When they do that, they overshoot, creating high pressure, and so on. We can look at those high and low pressure ways of starting sounds, contrasting a couple of things you can do with your mouth. To do that, I'm going to hop over to the PROT program, which looks like I think it looks like an ear with a pink hat on it, but I guess that thing is supposed to be a mouth up at the top. PROT is a free speech software tool that we will use a fair amount in class. You'll get a first chance to do that when we get together in class to do some exercises. I am going to record a sound on PROT. And is this working or not? It is working. Okay, so I can make a sound and I can make a sound, and then I can go look at them. Alright, so let's see here. If I click in this gray bar, I can play what I've recorded. It is working. Okay, so I can make a... Alright, so right here is that pop sound, and if I go take a look at that, you can see these waving cycles of air pressure that are the result of me generating that sound with my lips. Sounds kind of funny all by itself. All right, and then this is probably my clicky sound here. Maybe I'll zoom in a little bit closer. Okay, and again, here we can see these cycles of the pressure being higher than atmospheric pressure as recorded at the microphone I'm wearing on my head, versus the air being lower than the atmospheric pressure as recorded on the microphone on my head. Both of these sounds were kind of odd ones. They had very abrupt onsets, going from more or less nothing to these initial changes in pressure. Most of the speech we look at isn't going to quite look like this, though what we have here isn't too different from something like a t sound that you would have for the release of a stop. Okay, so we were already looking a little bit at a sound pressure waveform graph in PROT. So in this graph we have two dimensions. There's the amplitude dimension going up and down. There's the time dimension going across the bottom. Usually, though we can also look at how a wave fills in a space, like how it propagates across a room, in which case we could look at a distance from the speaker making that sound as opposed to looking at the time of that sound at a particular point. Whichever way we do it, time or distance, the waveform basically looks the same. The only difference really is what physical dimension we're measuring those changes in amplitude, those changes in pressure over. So when pressure is above atmospheric pressure, we have areas of compression. When it's below atmospheric pressure, we have rarefaction. One cycle of that wave can go from basically equivalent points in that repeating pattern. So in this case, it's from one peak to the next. I have two descriptions of that cycle up here. One is the period, which is the duration of a cycle in terms of time. The other is wavelength, which is the physical length that one wave of the sound fills up in space as it propagates around. Again, this graph looks kind of like a transverse wave where things are going up and down relative to the direction of propagation of the wave. But what sound really looks like is down here on the bottom with these dots. Areas of compression where there's more air molecules squished together creating high pressure, and areas of rarefaction where there's fewer air molecules squished together creating lower air pressure. Okay, so repeating all that again a little bit, we have the y-axis up the side with our amplitude of our sound in terms of pressure in any of the various units that we could use. But in the case of most things that we look at in a recording, it's been recorded by a microphone. And the way that recording happens is the head of the microphone gets pushed by the air pressure. The movement of that head creates an electrical current. And so the thing that's really measuring how loud that sound is some sort of electrical measurement inside of the computer. In the case of Prot, since you don't necessarily have calibrated equipment that you're making recordings of, there's no attempt to give you a true measure of the amplitude or the intensity of a sound. It just shows a relative scale from -1, the lowest pressure that the microphone can pick up, to +1, the highest pressure that the microphone can pick up, with no units involved. Almost all of the time when we're looking at waveforms, we are looking at the sound pressure that's measured at a particular point in space, like the microphone that is recording the sound, and how that changes over time. And once again, 0 in this graph is atmospheric pressure. The sound pressure may be positive, higher in cases of compression, or lower, negative in cases of rarefaction. In the case of looking at this again in something like Prot, here it is, I can create a sound, which is something you guys will be doing in class as an exercise and then for homework, in a variety of ways. I'll just choose this first one here in the sound menu to create a sound. Got a whole bunch of stuff in here that we will learn all the ins and outs of eventually. Start and end time tells us how long it is. There's some computery stuff. There is an amplitude Pascal thing in here, but I'll just go ahead and take whatever the defaults are and say OK. And then for that sound, go and look at it. And I get something that looks a lot like the graph that we were just looking at on that slide with peaks and troughs. I'm actually going to go up to pulses and turn that off, and that'll take away those blue marks for now. So this is showing me my compression of the microphone head and rarefaction on the microphone head in cycles over time as this sound is hitting the microphone or projected by a speaker. In this case, I created this thing synthetically on a computer, just using that prot command, but I can play it for us to listen to. Played it 3 times there. Sounds like a tone you might have in a hearing exam or something. I have one other thing in this display that I probably should have turned off before I started, which is this extra little blue line down here that's in my pitch menu. So I'm going to turn that off too. So if you tried doing this at home and didn't touch much of anything else in Prot other than to create the sound and look at it, your display would probably look kind of like this. So if you want to practice, you could give that a shot. We'll do a few examples of this in class where I'll demonstrate that again and also provide you with instructions for you to try doing it yourself with everything written out step by step.